Why would a real wormhole be a total nightmare? You are standing at the mouth of a wormhole. It hangs in space before you like a sphere of stolen light, roughly 40 meters across, hovering in the vacuum about 200,000 kilometers from Earth. Your ship drifts closer. Through your forward viewport, you can see it clearly now, and the sight turns your stomach in ways that no amount of astronaut training could have prepared you for. The sphere is not dark. It is not a shadow or a void. It is something far stranger. It is blazing with the light of another place entirely. Stars you have never seen before shimmer across its surface, arranged in constellations that belong to a sky billions of kilometers away. The distortion around the edges is nauseating. Light from the stars behind the wormhole bends and swirls, twisted into arcs and rings by the ferocious warping of space-time. It looks as though someone has taken a chunk of the universe and folded it, punching a hole through the crease. Mission Control gives you the signal. Your heart rate spikes. Your co-pilot reads the checklist one more time, and you both know, deep in the pit of your stomachs, that the checklist is a formality. Nobody has ever done this before. Nobody truly knows what lies inside. You fire the engines. The ship accelerates gently toward the sphere. As you approach, the image of that far-off patch of sky grows larger and clearer, filling more and more of your vision, until the entrance swallows you whole. And that is when the nightmare begins. Because everything that science tells us about wormholes, every equation, every simulation, every thought experiment conducted by every brilliant mind that has ever turned its attention to these hypothetical tunnels through space-time points to the same unsettling conclusion. A real wormhole would not be the cosmic shortcut of your dreams. It would be a death trap, a cosmic torture chamber, a structure so fundamentally hostile to anything that dared to pass through it that the universe itself seems to have conspired to make them impossible. This is not a story about the wonder of theoretical physics, though we will encounter plenty of wonder along the way. This is a story about what happens when you take one of science fiction's most beloved ideas and hold it up against the cold, unflinching light of actual physics. It is a story about tidal forces that would pull your atoms apart, about exotic matter that may not exist anywhere in the cosmos, about tunnels that collapse faster than light can travel through them, about time paradoxes so severe that the universe would rather destroy the wormhole than allow them to occur, and about the deeply unsettling possibility that even if you somehow solved every single one of these problems, the wormhole might still be slower than just flying through regular space. So settle in, get comfortable, because we are about to take the longest shortcut in the universe, and by the end, you will understand exactly why nature has gone to such extraordinary lengths to keep these things from ever working. Let us begin where all good stories about the fabric of reality begin, with a quiet patent clerk in Switzerland and the most dangerous equation ever written, the machine that builds nightmares. In 1915, Albert Einstein changed the way humanity understood gravity forever. Before Einstein, gravity was simple. Isaac Newton had described it as a force, an invisible pull between objects that had mass. The Earth pulls on the moon. The sun pulls on the Earth. An apple falls from a tree because the planet beneath it is tugging it downward. Newton's law of universal gravitation was elegant, practical, and for more than 2 centuries, it worked beautifully. It guided the calculations of astronomers, helped engineers build bridges, and predicted the orbits of planets with remarkable precision. But Newton's gravity had a problem. It could not explain everything. The orbit of Mercury, the closest planet to the Sun, wobbled in ways that Newton's equations could not account for. Light, which has no mass in the Newtonian sense, should not be affected by gravity at all, and yet there were hints that starlight did bend when it passed near massive objects. And perhaps most troubling of all, Newton himself never explained what gravity actually was. He described how it behaved. He could tell you how strongly two objects attract each other based on their mass and distance, but he never told you why. The mechanism was a mystery, and Newton was honest about it. He wrote, famously, that he framed no hypotheses about the nature of gravity itself. Einstein provided the answer, and in doing so, he revealed that gravity was not a force at all. It was geometry. In Einstein's general theory of relativity, space and time are not the fixed, immutable stage upon which the drama of the universe plays out. They are part of the drama. Space and time are woven together into a single four-dimensional entity called space-time, and this space-time is not rigid. It bends. It warps. It curves and deforms in response to the presence of matter and energy. A star sitting in space does not reach out and pull on a nearby planet with some invisible rope. Instead, the star's mass creates a depression in the fabric of space-time itself, a kind of curvature, and the planet follows the path that this curvature dictates. The planet is not being pulled. It is simply moving along the most natural route through a landscape that has been reshaped by the star's presence. The physicist John Archibald Wheeler, whom we will meet several more times in this story, summed it up with a phrase that has become one of the most quoted lines in all of physics. Matter tells spacetime how to curve, and spacetime tells matter how to move. This idea is beautiful, and it is also incredibly powerful. General relativity explained Mercury's wobbling orbit perfectly. It predicted that light would indeed bend around massive objects, a prediction confirmed during a solar eclipse in 1919 that made Einstein a global celebrity overnight. It predicted gravitational waves, ripples in the fabric of space-time itself created by colliding black holes and neutron stars, which were finally detected a century later by the LIGO experiment in 2015. It predicted the expansion of the universe, the existence of black holes, the slowing of time near massive objects, and a dozen other phenomena that have since been confirmed with extraordinary precision. But general relativity is more than just a physical theory. It is, as the transcript of our reference material so perfectly describes it, a machine. You start with an input, a particular arrangement of matter and energy. You feed that input into the equations of general relativity, and out pops an answer, a prediction for how that arrangement of matter will behave under the influence of its own gravity. The equations do not care whether the arrangement you fed in is realistic. They do not care whether the scenario you described could ever actually occur in nature. They simply process the input and deliver the output, faithfully and without judgment. If you ask the machine what happens when a massive star runs out of fuel and collapses under its own weight, the machine tells you about black holes. If you ask the machine what happens to two neutron stars spiraling toward each other, the machine tells you about gravitational waves. And if you ask the machine what happens when you arrange space-time in just the right way, connecting two distant points through a tunnel in the fabric of reality itself, the machine tells you about wormholes. The machine does not tell you whether wormholes are real. That part is up to you. And as it turns out, the answer is deeply, terrifyingly complicated. Because the machine of general relativity does not just produce one type of wormhole, it produces several, and each one of them is a nightmare in its own unique way. To understand why, we need to go back to the very beginning, to the first time anyone ever looked at Einstein's equations and saw a tunnel where they expected to find a dead end. We need to go to Princeton, New Jersey, in the year 1935, and meet the man who accidentally invented the bridge to another universe. The bridge that was never meant to be crossed. Nathan Rosen was 25 years old when he knocked on Albert Einstein's door. It was 1934, and Rosen had recently arrived at the Institute for Advanced Study, which had been established on the grounds of Princeton University just a few years earlier. The institute was a haven for some of the finest minds in mathematics and physics, a place where scholars could think without the burden of teaching or administration. And at the center of it all, like a sun around which the entire intellectual solar system orbited, was Einstein himself. Rosen was smart. He had earned his doctorate from the Massachusetts Institute of Technology during the depths of the Great Depression, and he had already published several noteworthy papers, including one that proposed a largely correct model of the atomic nucleus before neutrons had even been officially discovered. He was capable, hardworking, and intensely curious about the intersection of gravity and electromagnetism, a subject that consumed much of Einstein's later career. But he was also nervous. Einstein was the most famous scientist on the planet, and Rosen was just a young researcher hoping to make a good impression. When he finally gathered the courage to visit Einstein's office, he found the great man deep in conversation with another collaborator, the mathematician Walter Mayer. Rosen later recalled the encounter with characteristic modesty. I told him about my work on the solutions of the equations of his unified field theories, and he seemed interested and asked many questions. After a while, he began telling me about the work he was doing at the time, and before I realized it, the three of us were engaged in a lively discussion of his current problems. What followed was a 3-year partnership that would produce some of the most enduring ideas in theoretical physics. Officially, Rosen was Einstein's assistant. In practice, their relationship was something closer to a friendship, bound together by a shared fascination with problems that most other physicists considered foolish or impractical. Einstein was trying to unify gravity with electromagnetism, a quest that the broader physics community regarded with skepticism verging on pity. Rosen was one of the few who took the effort seriously, and that shared conviction deepened their bond. It was during this period that Rosen proposed an idea that would, decades later, become one of the most famous concepts in all of physics. Einstein had been frustrated, deeply frustrated, by the appearance of singularities in his equations. A singularity is a point where the mathematics breaks down, where quantities shoot off to infinity and the equations simply stop making sense. The Schwarzschild solution, the first exact solution to Einstein's field equations found by the German physicist Karl Schwarzschild in 1916 while he was serving in the trenches of World War I, described the gravitational field around a simple, spherical mass like a star. But it contained a disturbing feature. If you compressed that mass below a certain critical size, the solution predicted a singularity, a point of infinite density surrounded by a boundary from which nothing, not even light, could escape. Einstein detested singularities. He viewed them as signs of a flawed theory, ugly blemishes on the elegant face of general relativity. He wanted to find a way to eliminate them, and Rosen had a radical suggestion. What if, instead of reaching the singularity, a line falling into this compressed mass could keep going? What if mathematics allowed a traveler to avoid the singularity entirely, following a path that looped around it and emerged somewhere else? Rosen had just the tool to explore this question, general relativity itself. And when he and Einstein worked through the calculations, they found something remarkable. The path did not end at the singularity. Instead, it formed a bridge, a smooth geometric connection between two separate regions of space-time. You could follow this path inward, through the region that would later be called the event horizon, around the singularity, and out into what appeared to be an entirely different part of the universe. To complete their theory, Einstein and Rosen added electromagnetic fields to the equations, hoping that this bridge construction might also explain the nature of subatomic particles. They imagined that particles could be described as these geometric bridges in space-time, tiny tunnels connecting different regions of the fabric of reality. The attempt ultimately did not succeed on that front, but the bridge itself survived in the scientific literature. It was published in July 1935 in a paper titled The Particle Problem in the General Theory of Relativity, and it would come to be known as the Einstein-Rosen bridge. Einstein and Rosen did not invent wormholes. They did not use that word, and they did not envision their bridge as a means of transportation. In fact, as later physicists would discover, the original Einstein-Rosen bridge was not traversable at all. It was a mathematical construction, a way of connecting two copies of space-time in a manner that avoided the dreaded singularity. But the seed had been planted. Somewhere in the cold machinery of general relativity, there existed a solution that described a tunnel through space and time. And once that idea entered the world, it would never leave. It would take decades and the efforts of dozens of brilliant physicists to understand what the Einstein-Rosen bridge truly meant. Some would try to use it to travel across the cosmos. Others would try to use it to travel through time. And all of them, without exception, would discover that the universe had set traps along every path. But before we can understand those traps, we need to understand the bridge's strange twin, an object so bizarre, so fundamentally at odds with the laws of physics as we know them, that most scientists refuse to believe it can exist. We need to talk about white holes, the mirror that should not exist. There is a peculiar symmetry built into the heart of general relativity, one that Einstein himself understood but never fully embraced. The equations of gravity do not know which direction time flows. Think about what that means for a moment. If you filmed the ball being tossed into the air and played the footage backward, you would see a ball rising and then falling. Both versions of the footage, forward and backward, look perfectly natural. The mathematics of gravity, the equations that describe the ball's trajectory, work identically in both directions of time. You could not look at the equations alone and determine which way the clock was ticking. This property is called time reversal symmetry, and it has profound consequences for the objects that general relativity describes. A black hole is a particular solution to Einstein's equations. It is a region of space-time where gravity is so intense that nothing, not even light, can escape. Matter falls in. Nothing comes out. The event horizon is a one-way door, open only inward. But if the equations do not care about the direction of time, then there must be another solution, the time-reversed version of a black hole. A region of space-time where nothing can enter, but from which matter and energy are relentlessly expelled outward. A cosmic geyser, blasting radiation and particles in every direction, surrounded by a boundary that forbids entry with the same absolute authority that a black hole's event horizon forbids escape. This object is called a white hole, and it was first described in the 1960s by Soviet astronomer Igor Novikov. Novikov had been born in Moscow in 1935 and had risen quickly through the ranks of Soviet academia, eventually reaching leading positions at Moscow universities despite the considerable challenges of working as a physicist behind the Iron Curtain. Research in the Soviet Union was a tricky affair. You had to ensure that your work did not conflict with state ideology. You could be pulled away from your research at any moment to work on some government-mandated priority, and you had almost no hope of sharing your discoveries with the broader international scientific community. Despite all of this, Novikov had enough intellectual freedom to pursue some deeply unconventional lines of inquiry. And in 1964, he made a simple but profound observation about gravity. Since general relativity's equations work the same way forward and backward in time, a black hole's equations could be run in reverse. Instead of a region that trapped particles forever, you would get a region that ejected particles forever. Instead of a black hole, you would get a white hole. A white hole would be one of the strangest objects the universe could conceivably produce. It would still have a singularity at its center, just like a black hole. It would still have mass, so you would still feel gravitationally attracted to it. But you could never, ever enter one. The boundary surrounding a white hole, sometimes called an anti-horizon, works in the opposite direction from a black hole's event horizon. Where the event horizon forbids outward travel, the anti-horizon forbids inward passage. It is the ultimate members-only club, and the guest list is permanently closed. If you found yourself inside a white hole when it first formed, perhaps trapped there from the very beginning, you would not stay there for long. You would be pushed outward, propelled at speeds approaching and even exceeding the speed of light, flung out like a cork from a champagne bottle, unable to resist the relentless outward current of space-time itself. The white hole would continue vomiting matter and radiation until it had emptied itself completely, leaving behind nothing but a bare singularity and its impenetrable anti-horizon. Novikov originally proposed white holes to explain mysterious bright sources that were appearing in astronomical surveys. He thought these blazing beacons of light might be white holes, cosmic fire hoses spraying energy into the universe. But his work, conducted behind the Iron Curtain, was largely unknown to Western scientists for years. In time, physicists would find a more mundane explanation for those bright sources. They were quasars, powered not by white holes, but by the colossal energies released when matter spirals into the gravitational maw of supermassive black holes. The white hole hypothesis faded from prominence, but it never quite disappeared because white holes serve a critical role in the theory of wormholes. If you want to build a tunnel through space-time, you need a black hole at one end and a white hole at the other. The black hole is the entrance. The white hole is the exit. The Einstein-Rosen bridge connects them through a passage in the geometry of space-time. There is just one devastating problem. White holes almost certainly cannot exist. The reason comes from a branch of physics that general relativity ignores entirely: thermodynamics, the science of heat, energy, and disorder. General relativity does not care about the direction of time, but thermodynamics very much does. The second law of thermodynamics states that in any natural process, the total entropy, the total disorder, of a closed system must either increase or stay the same. It can never decrease. Eggs break, but do not unbreak. Ice melts, but does not spontaneously freeze in a warm room. The universe marches relentlessly toward greater disorder, and this march is what gives time its arrow, its clear and unmistakable direction from past to future. A black hole is perfectly consistent with the second law. When matter collapses to form a black hole, entropy increases. Everything is fine, but a white hole is the time reversal of this process. For a white hole to form, entropy would have to decrease. Order would have to spontaneously emerge from disorder. That broken egg on the floor would have to reassemble itself and leap back onto the counter. And the second law of thermodynamics says that cannot happen, not naturally, not ever. There is no known mechanism in the entire framework of modern physics that can create a white hole. When a star collapses, the cascade of forces and energies that produces a black hole simultaneously pinches off the possibility of a white hole forming. It is as if the universe slams the door on white holes at the very moment it opens the door to black holes. And even if, through some miraculous or exotic process, a white hole were somehow created, perhaps as a remnant of the Big Bang or through some yet-to-be-discovered quantum phenomenon, it could not survive for long. Remember, a white hole still has mass. It still warps space-time around it. Anything in the vicinity would be gravitationally attracted to it. But nothing can enter the anti-horizon. So you would get closer and closer, pulled by gravity toward the boundary, but unable to cross it. The energy of this system, of you being drawn infinitely close to the anti-horizon without ever passing through, builds and builds and builds. It grows without limit, and eventually, the system becomes catastrophically unstable. To put it simply, it explodes. A white hole is a bomb with a lit fuse from the moment of its creation. It cannot be sustained. It cannot be stabilized. And without a stable white hole to serve as the exit, the entire concept of an Einstein-Rosen bridge as a traversable tunnel falls apart. For decades, this seemed like the end of the story. Wormholes were a mathematical curiosity, nothing more. Beautiful solutions to Einstein's equations that had no counterpart in the real universe. The entrance, a black hole, was real enough. We have observed them, photographed them, detected the gravitational waves from their collisions. But the exit did not exist, and without an exit, there is no tunnel. There is only a one-way trip to oblivion. But physicists, like explorers, have never been particularly good at accepting dead ends. And the man who would breathe new life into the idea of wormholes was, appropriately enough, someone who had been asking dangerous questions since he was 4 years old. The man who named the nightmare. John Archibald Wheeler's mother liked to tell a story about her son. When he was 4 years old, splashing around in the bathtub one afternoon, he suddenly went still. The splashing stopped. The playful noise ceased. He looked up at her with an expression of intense concentration and asked a question that most 4-year-olds would never think to pose. What happens when you get to the end of things? It was a question that would define his entire life. Wheeler grew up to become one of the most imaginative and daring physicists of the 20th century, a man who had an almost pathological inability to leave a question unasked or a possibility unexplored. He coined the term black hole. He popularized the phrase about matter telling space how to curve. He trained an entire generation of brilliant physicists, including Kip Thorne, who would later win a Nobel Prize. And he never lost the childlike energy that had produced that bathtub question, including a particular fondness for racing down flights of stairs as quickly as his legs would carry him, a habit he maintained well into old age. It was Wheeler who took Nathan Rosen's obscure bridge and gave it a new name, a name that would capture the public imagination and refuse to let go. In the 1950s and 1960s, as Wheeler explored the implications of Einstein's equations with the same boundless curiosity that had driven his bathtub inquiry, he realized that the Einstein-Rosen bridge was not just a static mathematical structure. It was a tunnel, a shortcut, a passage through the geometry of space-time that, in principle, could connect 2 points separated by vast distances. He called them wormholes. The name was perfect. It evoked the image of a worm burrowing through an apple, taking a shortcut from one side of the fruit to the other instead of crawling all the way around the surface. In the same way, a wormhole could connect 2 distant points in the universe through a tunnel that was far shorter than the journey through normal space. You could step in at one end and emerge at the other, having traveled millions or even billions of light years in what might feel like a short stroll. It was a thrilling idea. It was also, Wheeler quickly realized, a lethal one. The problem was stability, or rather, the complete and utter lack of it. Wheeler examined the dynamics of the Einstein-Rosen bridge, not as a frozen snapshot in time, but as a living, evolving structure in the full 4-dimensional framework of general relativity. And he discovered something devastating. The bridge did not hold. Remember, the interiors of wormholes are not the serene, glowing tunnels depicted in science fiction. They are regions of space-time under unimaginable stress. Gravity inside a wormhole does not merely pull straight inward, the way it does around a planet. It also tears. It stretches and compresses and distorts, exerting what physicists call tidal forces. These are the same forces that cause ocean tides on Earth, generated by the difference in gravitational pull between the near and far sides of an object. The moon tugs on the side of the Earth facing it more strongly than on the far side, and this difference creates the gentle rise and fall of the seas. But there is nothing gentle about the tidal forces inside a wormhole. They are monstrous. They would stretch you along the length of the tunnel, and crush you across the middle, pulling your body apart like taffy while simultaneously squeezing your sides inward. Physicists have a darkly humorous term for this process when it occurs near black holes: spaghettification. Your body would be drawn out into a long, thin strand, a noodle of atoms where a person used to be. And the tidal forces do not just affect travelers. They affect the wormhole itself. Wheeler's analysis showed that these gravitational stresses would compel the wormhole to stretch along its length and compress across its middle, just like a rubber band pulled too far. The tunnel would narrow, the walls would rush inward, and then the wormhole would rip itself apart in a catastrophic collapse of gravitational energy. This collapse, Wheeler found, happens faster than the speed of light. Let that sink in. Nothing, no signal, no particle, no beam of light can travel through the throat of a wormhole and safely emerge from the other end before the tunnel destroys itself. The wormhole is born, and it dies, in a flash so brief that even photons, the fastest things in the universe, cannot outrun it. For a brief, tantalizing moment, you might glimpse a view of your destination. Light from either end of the wormhole can fall inward, and so you could see the universe at both your origin and your endpoint. If someone entered from the opposite side at the same time, you could even meet inside the tunnel. You could share stories. You could exchange photographs of skies separated by 1,000 galaxies. You could look each other in the eye and know that you were connected across distances that no other means of travel could possibly bridge. And then the wormhole would collapse. The tunnel walls would slam shut, and you would find yourself trapped inside what was, for all practical purposes, a black hole. The singularity would be your only possible destination. You would die? Wheeler's pronouncement was grim, and most physicists accepted it. Wormholes, it seemed, were literal dead ends. They were mathematical ghosts haunting Einstein's equations, beautiful and impossible and deadly. The dream of a cosmic shortcut was over before it had truly begun. But of course, it was not over. Because decades later, one of Wheeler's own students would find a way to keep the tunnel open. He just needed a little help from the most famous science fiction writer of his era and a substance that might not exist anywhere in the universe. A phone call that changed everything. In 1985, Kip Thorne received a phone call that would alter the course of theoretical physics. Thorne was, by that point, one of the most respected relativists in the world. He had studied under Wheeler himself, absorbing his mentor's boundless curiosity and fearless approach to the deepest questions in physics. He had become the Feynman Professor of Theoretical Physics at the California Institute of Technology, and he had spent years working on gravitational waves, black holes, and the warped geometry of extreme space-time. The call was from his friend Carl Sagan. Sagan was writing a novel. The book, which would eventually be published as Contact and later adapted into a film starring Jodie Foster, told the story of humanity receiving a signal from an alien intelligence, a signal that contained blueprints for a machine. The machine, once built, would allow a team of scientists to travel to a distant star system. Sagan needed a scientifically plausible mechanism for this journey, and his first instinct had been to send his protagonist through a black hole. But Sagan was a rigorous scientist, not just a storyteller, and he wanted to make sure the physics was defensible. So he turned to Thorne for advice. Could a person travel through a black hole and emerge in another part of the galaxy? Thorne's answer was a firm no. A black hole is a trap, not a tunnel. Anything that crosses the event horizon is doomed to meet the singularity. There is no coming back, no emerging on the other side, no shortcut to the stars. The physics was unambiguous on this point. But Thorne, true to the spirit of his mentor Wheeler, did not just refuse and hang up the phone. Instead, he thought about it. He thought about what kind of structure could serve as a shortcut through space-time. He thought about the Einstein-Rosen bridge and about Wheeler's discovery that it collapsed too quickly to be traversed. And he asked himself a question that nobody had thought to ask quite so directly before. What would it take to keep a wormhole open? This was the critical insight. Previous physicists had examined wormholes as they naturally occurred within the framework of general relativity, as structures built from the geometry of black holes and white holes, and found them wanting. Thorne took a different approach. Instead of asking what wormholes the equations naturally produced, he asked what kind of matter and energy would be required to produce a specific desired structure, a stable, traversable wormhole. It was like working the machine of general relativity in reverse. Normally, you specify the matter and energy, and the equations tell you what the resulting space-time geometry looks like. Thorne started with the geometry he wanted, a tunnel through space-time with an entrance outside any event horizon and walls that did not collapse, and asked the equations what configuration of matter and energy was required to build it. The machine of relativity, ever dutiful, provided an answer. Negative mass, not antimatter, which has positive mass but opposite charge. Not dark matter, which has positive mass but does not interact with light. Negative mass, a substance that weighs less than nothing. A football that tips the scales at minus 500 grams. A cut of meat from the butcher that registers minus 2 kilograms on the scale. Negative mass would behave in ways that defy every intuition you have about how the physical world works. While ordinary mass attracts, negative mass repels. While ordinary mass pulls space-time together, negative mass pushes it apart. If you fashion negative mass into a shell and placed it at the throat of a wormhole, the repulsive pressure it generated would inflate the entrance, pushing it beyond the event horizon and allowing you to enter the tunnel without being swallowed by the singularity at its heart. That same pressure would prop the tunnel walls open, resisting their natural inclination to collapse, allowing objects, light, particles, even spaceships, to pass through. In 1988, Thorne published these findings in a landmark paper co-authored with his student Michael Morris. The paper was titled Wormholes in Space-Time and Their Use for Interstellar Travel, a tool for teaching general relativity. The subtitle is important. Thorne was careful to present this work not as a serious proposal for building a wormhole, but as a teaching exercise, a way to engage students with the deep and beautiful mathematics of general relativity by applying it to a problem that captured the imagination. But the imagination, once captured, tends to run wild. The paper ignited a firestorm of interest in traversable wormholes, launching decades of research, thousands of papers, and an entirely new subfield of theoretical physics. Thorne's work gave the world, for the first time, a concrete recipe for a wormhole that a human being could survive passing through. There was just one catch, a rather enormous one. The recipe called for an ingredient that nobody had ever found, that nobody knew how to make, and that, if it existed, would break some of the most fundamental principles in all of physics. The impossible ingredient. Exotic matter, as physicists came to call the negative mass substance required to stabilize a traversable wormhole, has never been observed. Not in any laboratory on Earth. Not in any telescope survey of the sky. Not in any particle accelerator experiment, any cosmic ray shower, any supernova remnant, any galactic core. Decades of searching have produced exactly zero evidence that matter with negative mass exists anywhere in the universe. And there are excellent theoretical reasons to believe that it cannot. Consider what negative mass would actually mean for the world around you. If you kicked a football made of negative mass, it would fly backward, toward your foot, not away from it. The force you applied would produce acceleration in the opposite direction. If you dropped it, it would fall upward, rising into the sky instead of hitting the ground. These bizarre behaviors are not just strange. They violate the conservation of momentum, one of the most tested and verified principles in all of physics. Conservation of momentum is the principle that says the total momentum of a closed system remains constant unless acted upon by an external force. It is the reason why a rocket moves forward when it expels exhaust backward. It is the reason why a billiard ball transfers its motion to another ball when they collide. It undergirds virtually every single theory of modern physics, from classical mechanics to quantum field theory. If negative mass existed and behaved the way the equations say it must, this foundational principle would crumble. Now, it is perfectly possible that our understanding of momentum conservation is incomplete or inadequate in some extreme regime that we have not yet explored. Physics has a long history of revising its foundational principles in the face of new evidence. Newton's absolute space and time gave way to Einstein's relative space-time. Classical determinism gave way to quantum probability. But momentum conservation has survived every test thrown at it for centuries. There are no cracks in it, no anomalies, no unexplained deviations. It is as rock solid as physics gets. So exotic matter with negative mass seems like a dead end. But Einstein showed us that mass and energy are two sides of the same coin, related by his famous equation. If we cannot find negative mass, perhaps we can find negative energy. And as it happens, nature provides a tantalizing hint that negative energy might, under very specific and limited circumstances, actually exist. This hint comes from a phenomenon called the Casimir effect, and its discovery has one of the more charming backstories in 20th century physics. Shortly after the Second World War, a young graduate student named Hendrik Casimir was working in Copenhagen under the legendary Niels Bohr, one of the founding fathers of quantum mechanics. But Bohr, in his characteristically eccentric fashion, had temporarily diverted Casimir away from hard physics to test a pet hypothesis about human reaction times. Bohr believed that automatic responses were faster than intentional ones, a concept now known as the gunslinger effect, and to test this, he organized mock gunfights in the streets of Copenhagen, with graduate students facing off against each other with pretend weapons while Bohr timed them with a stopwatch. Casimir, presumably, would rather have been working on quantum field theory. But sometimes the best ideas come from unexpected places, and perhaps the image of two people staring at each other across a small distance, tension building in the space between them, stuck in his mind. Because when he returned to his calculations, he produced one of the most remarkable results in quantum physics. Casimir showed that if you place two uncharged metal plates very close together in a vacuum, with nothing between them at all, they will spontaneously move toward each other. Not because of any conventional force, not because of electrostatics or magnetism or gravity, but because of something far more fundamental. Quantum mechanics tells us that the vacuum, what we call empty space, is not truly empty. It is seething with activity. Quantum fields permeate all of space and time, and these fields are constantly vibrating, producing fleeting disturbances called virtual particles that pop into existence and vanish again in intervals so brief they escape direct detection. In the open vacuum, all possible vibrations can occur, all possible wavelengths can exist. But between the plates, the situation is different. The plates impose boundaries. Only vibrations whose wavelengths fit neatly between the plates are permitted. Longer wavelengths, the ones that do not fit, are excluded. This means that there are fewer vibrations between the plates than outside them. Fewer vibrations means less energy. And because the space between the plates has less energy than the surrounding vacuum, the external pressure of the vacuum pushes the plates together. This is the Casimir effect, and it has been measured experimentally with extraordinary precision. In 1996, physicist Stephen Lamoureux confirmed Casimir's prediction to within 5% accuracy. The force is real. It exists. And because the energy density between the plates is lower than the energy density of the surrounding vacuum, It can be described, in a certain very specific sense, as negative energy. Here is where the story connects back to wormholes. Kip Thorne and his colleagues realized that a sufficient concentration of negative energy, like the Casimir effect, but amplified to a vastly greater degree, could in principle serve the same role as negative mass. It could push space-time apart at the wormhole's throat, holding the tunnel open and allowing safe passage. But the Casimir effect, as observed in the laboratory, is unimaginably small. It operates over distances of nanometers, producing forces measured in micronewtons. To stabilize a wormhole large enough for a person to pass through, you would need to scale this effect up by a factor so enormous that it beggars comprehension. You would need to violate the energy conditions, a set of rules that physicists have developed over decades to describe how energy can behave in the real universe. These energy conditions, the weak energy condition, the null energy condition, the strong energy condition, the dominant energy condition, are not derived from first principles. They are, in a sense, educated guesses, constraints based on everything we have observed about how gravity and energy interact. They state, among other things, that energy cannot travel faster than light, that local mass cannot be negative, and that gravity must always be attractive at small scales. The Casimir effect violates the weak energy condition, but only in the extremely localized space between the plates. When you zoom out and average over a larger volume that includes the plates and their surroundings, the total energy is positive and the violation disappears. Whether these energy conditions can be violated at large scales, the kind of scales you would need for a traversable wormhole, is an open question. Nobody has proven it is impossible. Nobody has proven it is possible, either. And so we arrive at the first great nightmare of real wormholes. To build one, you need a substance that physics has never produced and may never be able to produce. You need energy that behaves in ways that violate the rules we have observed governing every other form of energy in the universe. You need, in essence, a miracle of engineering built on a foundation of physics that may not exist. But suppose, for the sake of argument, that you got your miracle. Suppose some impossibly advanced civilization found a way to generate negative energy on a macroscopic scale, fashioned it into the precise configuration required by Thorne's equations, and built a stable, traversable wormhole. Suppose you stepped inside, sailed through the tunnel without being crushed or stretched or torn apart, and emerged on the other side. You would still have a problem, because a working wormhole is not just a bridge across space. It is also a tunnel into the past, the geometry of destruction. Before we confront the time travel problem, we need to understand in much greater detail exactly what would happen to a human body attempting to traverse any wormhole, even one that has been theoretically stabilized. Because the physical experience of wormhole travel is, to put it charitably, the single most hostile environment that physics can describe short of the interior of a singularity. Let us start with what physicists call tidal forces, because they are the most immediate and visceral threat. You are probably familiar with tides on Earth. The moon's gravity pulls on the side of the Earth facing it more strongly than on the far side, because gravity weakens with distance. This difference in gravitational pull, this gradient, is what creates the ocean tides. The same principle operates near any massive object, but the strength of the effect depends on how steeply gravity changes over a given distance. Near a stellar mass black hole, the kind formed from the collapse of a massive star, the gravitational gradient is absolutely savage. The difference in gravitational pull between your head and your feet, assuming you are falling in feet first, would be enormous even at considerable distances from the event horizon. Physicists have calculated that a force of roughly 9,000 newtons, or about 2,000 pounds, is sufficient to pull a human body apart. For a black hole with the mass of our Sun and a Schwarzschild radius of about 3 kilometers, you would reach this lethal tidal force at a distance of roughly 700 kilometers from the center. You would be torn to shreds long before you reached the event horizon. For a human body falling feet first towards such a black hole, the tidal acceleration at the event horizon would be approximately 19.6 billion meters per second squared. To put that in perspective, the tidal acceleration you feel standing on the surface of the Earth, the gentle gradient between your head and your toes, is about 0.0000055 meters per second squared. The black hole's tidal force is roughly 3.5 trillion times stronger. This is spaghettification, the process by which an extended object near a black hole is stretched along its length and compressed across its width, drawn out like pasta through a cosmic extruder. Every atom in your body would be pulled in a slightly different direction, and the cumulative effect would be indescribably violent. Your body would not just break apart. It would be drawn into a thin filament of subatomic debris, a stream of particles miles long and thinner than a hair, spiraling down toward the singularity. Now, you might think that a traversable wormhole, stabilized by exotic matter, would avoid this problem. After all, the whole point of Thorne's design was to create a tunnel that a human could survive passing through. And in theory, this is correct. A properly designed wormhole, with the right configuration of negative energy, could have tidal forces at its throat that are manageable, even gentle, comparable to what you feel standing on Earth's surface. But here is the nightmare. The margin for error is essentially zero. The exotic matter must be arranged with absolute precision. Too little, and the wormhole's tidal forces remain lethal. Too much, and the geometry of the tunnel distorts in unpredictable ways, potentially creating new singularities within the passage or causing the wormhole to become unstable in entirely different ways. The balance is exquisitely delicate, and any perturbation, any slight asymmetry, any disturbance from a passing gravitational wave or a stray particle could tip the system from a gentle tunnel into a death trap. Thorne and Morris acknowledged this in their 1988 paper, listing 9 conditions that a traversable wormhole must satisfy. Among them, the tidal gravitational forces must be bearably small. There must be no event horizon, otherwise entry would be a one-way trip. The traversal time must be reasonable, both from the traveler's perspective and from the perspective of stationary observers. And the wormhole must be stable against small perturbations. That last condition is the killer. Stability against perturbation means that if a small rock or a photon or even a single atom deviates from the ideal trajectory while passing through the wormhole, the resulting disturbance must not grow. It must not amplify. It must not cascade into a feedback loop of gravitational disruption that tears the tunnel apart. In the language of physics, the wormhole must be dynamically stable, like a ball resting at the bottom of a bowl, always returning to its equilibrium state after being nudged. Most analyses of wormhole stability suggest that this is extraordinarily difficult to achieve. The exotic matter holding the tunnel open creates a configuration that is inherently precarious. Think of it as balancing a bowling ball on the tip of a needle. Any deviation from perfect balance, and the system collapses. For a wormhole, collapse means the tunnel closes and anything inside is crushed. There is another physical horror lurking in the geometry of a traversable wormhole, the blue shifting problem. When light falls into a gravitational well, it gains energy. Its wavelength shortens, shifting toward the blue end of the spectrum. This is called gravitational blue shift, and it is the inverse of the more commonly discussed gravitational redshift that affects light escaping from a massive object. Inside a wormhole, light passing through the tunnel from either direction would be blue shifted. The deeper you go into the throat, the more intense the blue shift becomes. For certain wormhole geometries, this blue shift can become extreme. Background radiation from the cosmic microwave background, harmless 3-degree Kelvin microwaves that fill all of space, could be blue shifted inside the wormhole into high-energy gamma rays. The gentle ambient glow of the universe could become a lethal torrent of radiation, cooking anything inside the tunnel. Even your own ship's headlights could be a problem. Light emitted from your vessel as you move through the wormhole could be blue shifted by the geometry of the tunnel, reflected off the walls or the exotic matter lining, and returned to you at higher energy. In an extreme scenario, this could create a runaway feedback effect, where light circulating through the wormhole amplifies itself into a burst of radiation intense enough to destroy the tunnel and everything in it. This is closely related to the mechanism by which Hawking proposed that time machines would self-destruct. The vacuum fluctuations that circle through a time-shifted wormhole are subject to the same blue shifting, and their energy builds with each loop until it becomes infinite, destroying the wormhole. But even in a wormhole that is not configured as a time machine, the blue shifting of ambient radiation remains a serious concern. So add radiation poisoning to the list of nightmares. Even in a stable, traversable wormhole lined with perfectly arranged exotic matter, the geometry of the tunnel itself could transform the gentle background radiation of the universe into a lethal weapon. The scale of the problem. Let us talk about numbers for a moment, because the scale of the engineering challenges associated with building a wormhole tends to get lost in the theoretical discussion. To create a wormhole large enough for a human to pass through, you would need a throat diameter of at least a few meters. The exotic matter required to hold this throat open would need to have a tension, a radial pressure pulling outward, comparable to the pressure at the center of a neutron star. Neutron stars are the densest objects in the known universe apart from black holes, with pressures in their cores reaching roughly 1 billion trillion pascals. Now think about what that means. The substance holding your wormhole open would need to exert a tension equivalent to the forces inside the most extreme stellar objects in the cosmos. It would need to do this continuously, without fluctuation, across the entire circumference of the wormhole's throat. And it would need to be made of a material with negative energy density, something that has never been observed in bulk anywhere in the universe. How much exotic matter would you need? Early estimates suggested truly absurd quantities, comparable to the mass of Jupiter or even the Sun converted entirely into negative energy. Later work by Matt Visser and others showed that, in principle, the amount of energy condition violation could be made arbitrarily small, but this required increasingly contrived wormhole geometries, tunnels so long and narrow that they would be impractical for any conceivable purpose. And the energy requirements are only part of the problem. You also need to somehow create the wormhole in the first place. General relativity permits the existence of wormholes, but it does not tell you how to make one. There is no known physical process that naturally produces a traversable wormhole. Black holes form from stellar collapse. White holes do not form at all, and wormholes connecting separate regions of space-time do not arise from any process that our current physics can describe. The quantum foam hypothesis offers a possible seed, a Planck-scale wormhole that might be inflated to macroscopic size. But even this speculative process faces enormous hurdles. The Planck length is 20 orders of magnitude smaller than a proton. Inflating a Planck-scale wormhole to human scales would be like enlarging a grain of sand to the size of the observable universe. The energies required for such inflation and the precision needed to maintain stability during the process stagger the imagination. Some physicists have suggested that cosmic strings, hypothetical one-dimensional defects in space-time that might have been produced during phase transitions in the early universe, could serve as seeds for wormholes. If cosmic strings with negative mass were generated in the first fraction of a second after the Big Bang, they might create the geometric conditions necessary for wormholes to form. But cosmic strings themselves are hypothetical. We have searched for them in the cosmic microwave background and in gravitational wave data, and found no evidence of their existence. At every turn, the practical challenges of building a wormhole are just as nightmarish as the theoretical ones. The engineering requirements are beyond anything our civilization could contemplate. The energy requirements dwarf anything we can produce. And the raw materials, exotic matter with negative energy density, may not exist. The Hawking Party and the final irony. On June 28, 2009, the legendary physicist Stephen Hawking held a party. He booked a room at the University of Cambridge. He laid out champagne and hors d'oeuvres. He set up a banner that read, "Welcome, time travelers." He waited. Nobody came. Hawking waited for several hours, sipping champagne alone in the empty room. And then, only after the party had ended, did he send out the invitations. The coordinates were precise: 52 degrees, 12 minutes, 21 seconds north latitude, 0 degrees, 7 minutes, for 0.7 seconds east longitude. The time was 12 noon Universal Time. It was a party for visitors from the future, and the invitations were distributed afterward. The logic was elegant. If time travel were possible, someone in the far future would eventually discover the invitation and travel back to attend. The empty room, Hawking suggested, was reasonable experimental evidence that time travel was not possible. But Hawking himself was not entirely convinced. He noted that copies of the invitation might survive for thousands of years, and that someday, someone living in the future might find one and use a wormhole time machine to attend. He left the door open, just a crack, for the possibility that the physics might eventually prove him wrong. The empty party is a fitting metaphor for the entire story of wormholes. The invitation has been issued. The mathematics is in place. The tunnels exist, at least in the equations of general relativity, as valid solutions to Einstein's field equations. The welcome banner is hung, the champagne is poured, and the coordinates are waiting. But nobody has come. The universe, for all its mathematical generosity in permitting wormholes to appear in its equations, has been ruthlessly parsimonious in actually producing them. Every pathway to a working wormhole is blocked by some fundamental obstacle: instability, exotic matter, time paradoxes, radiation, or the simple cruelty of a shortcut that is longer than the journey it replaces. And yet the invitations remain. The mathematics does not change. The solutions to Einstein's equations that describe wormholes are as valid today as they were when Nathan Rosen first proposed his bridge in 1935. They will be valid 1,000 years from now. The question is not whether the mathematics permits wormholes. The question is whether the universe does. Our current understanding of physics, based on general relativity, quantum field theory, and the accumulated experimental evidence of more than a century of research, leans strongly toward no. The consensus among most physicists is that traversable wormholes are not allowed by the full set of physical laws governing our universe. But this consensus rests on an incomplete foundation. We do not have a theory of quantum gravity. We do not fully understand the energy conditions or the circumstances under which they might be violated. We do not know the full implications of the ER equals EPR conjecture or the relationship between entanglement and spacetime geometry. Hawking's chronology protection conjecture may be right, or it may be that the laws of quantum gravity, when we finally discover them, contain surprises that nobody has yet imagined. Physics has been wrong before. Newton's absolute space and time seemed unassailable until Einstein showed they were merely approximations. The impossibility of splitting the atom was conventional wisdom until it was split. The universe's expansion was unthinkable until Hubble measured it. Over and over, the impossible has become the actual, and the unthinkable has become the obvious. Wormholes may ultimately prove to be permanently, irrevocably impossible. They may be the one idea that the universe simply will not allow, no matter how cleverly we rearrange the equations or how advanced our technology becomes. In that case, they will still have been invaluable, because the process of understanding why they are impossible has taught us more about the fundamental nature of reality than almost any other problem in physics. Or they may prove to be possible, in some form we cannot yet imagine, through physics we have not yet discovered, using principles we have not yet conceived. In that case, the nightmares we have cataloged in this video will not be obstacles. They will be engineering specifications, challenges to be overcome by civilizations with knowledge and technology far beyond our own. Either way, the journey has been extraordinary. From Einstein's stuffy office at Princeton to Casimir's mock gunfights in Copenhagen, from Wheeler's bathtub question to Hawking's empty party, the story of wormholes is the story of human curiosity at its most audacious. It is the story of minds that refuse to accept limits, that pushed the equations to their breaking point and then asked what lay beyond. It is the story of nightmares that turned out to be the universe's way of teaching us something new. And the lesson, as always, is that the universe is more wonderful and more terrifying than we know. It bends and warps and connects itself through geometries that strain our imagination. It hides tunnels in its equations and then fills those tunnels with traps. It tantalizes us with the promise of shortcuts and then reveals, grinning, that the shortcuts are longer than the road. But it never, ever stops inviting us to look deeper. The party is still going on. The champagne is still waiting. And somewhere, in a corner of physics we have not yet explored, the guests from the future might be getting ready to arrive. The black hole's hidden architecture. To truly appreciate why wormholes are nightmares, you need to understand what happens at the boundary between the known and the unknown, the event horizon of a black hole, because every wormhole begins or ends with one. An event horizon is not a wall. It is not a surface you can touch or stand on. It has no thickness, no texture, no physical substance of any kind. It is a boundary in space-time, a mathematical surface that divides the universe into two regions, the outside, where escape is possible, and the inside, where it is not. If you were falling toward a stellar mass black hole and you crossed the event horizon, you would feel nothing at the moment of crossing. No bump, no barrier, no flash of light. General relativity is emphatic on this point. The event horizon is locally indistinguishable from ordinary space-time. An astronaut falling through it would notice nothing unusual, at least not at the moment of crossing. The horror comes afterward. Once inside the event horizon, the geometry of space-time undergoes a transformation so alien that it defies everyday language. In the exterior of a black hole, you can move freely in 3 dimensions of space, forward and backward, left and right, up and down, while being carried inevitably forward through the single dimension of time. But inside the event horizon, space and time effectively swap roles. The radial direction, the direction toward the singularity, becomes time-like. Moving toward the singularity is no longer a matter of spatial direction. It is the passage of time. You can no more avoid the singularity than you can avoid tomorrow. This means that inside a black hole, the singularity is not a place in space. It is a moment in time. It is the future. Every path you can take, every direction you can aim, every maneuver you can attempt, leads to the singularity. It is your inescapable destination, as certain as death and considerably less pleasant. For a wormhole of the Einstein-Rosen type, the interior of this black hole is supposed to connect to a white hole, forming a bridge. But as we have discussed, this bridge is catastrophically unstable. It exists for a fleeting instant and then collapses, leaving you trapped in the black hole interior with the singularity as your only future. Even in Thorne's stabilized, traversable wormhole, the geometry near the throat retains echoes of this extreme space-time structure. The curvature is intense. The metric coefficients, the mathematical functions that describe how distances and time intervals are measured, change dramatically over short distances. Moving through the throat means passing through a region where the rules of space-time are stretched to their limits, where tiny errors in the exotic matter configuration could restore the lethal geometry of a collapsing tunnel. Imagine walking across a bridge suspended over a bottomless chasm. The bridge is narrow and the wind is fierce. With each step, the planks shift slightly beneath your feet. This is what traversing a stabilized wormhole would be like, except the chasm is the singularity, the wind is the gravitational tidal force, and the shifting planks are fluctuations in the exotic matter holding the tunnel open. One wrong step, one stray vibration, and the bridge disappears beneath you. This architectural fragility is not a minor technical problem that might be solved by better engineering. It is a fundamental feature of the space-time geometry. Wormholes exist at the ragged edge of what general relativity permits, in a regime where the slightest perturbation can push the solution from stable to catastrophic. They are, by their very nature, structures balanced on the knife's edge between existence and annihilation. The Novikov principle and the universe's strange consistency. Let us spend a little more time with Novikov's self-consistency principle because it raises questions that are genuinely disturbing in their implications. Novikov proposed that if time travel through wormholes is possible, the universe must enforce consistency. The past cannot be changed. Events must unfold in a manner that creates no contradictions, even if a time traveler is present. This sounds reasonable in the abstract, but consider what it means in practice. Suppose you travel through a wormhole into the past, carrying a bomb. You intend to destroy a building that, in your original timeline, was not destroyed. According to Novikov's principle, you will fail. Something will prevent you. The bomb will malfunction. You will trip and drop it. A sudden storm will blow you off course. A stranger will intervene. The universe will conspire, through an improbable but not impossible sequence of events, to ensure that the building survives. Now scale this up. Imagine millions of time travelers, each attempting to change the past in different ways. Novikov's principle requires that every single one of them fails, that the universe produces an unbroken chain of coincidences, equipment malfunctions, natural disasters, and unlikely encounters, all perfectly orchestrated to preserve the consistency of history. This raises a profound philosophical question. Is the universe actually capable of this? Is there some mechanism, some law of physics we have not yet discovered that enforces self-consistency? Or is the self-consistency principle simply a statement about which histories are possible, a selection rule that eliminates all timelines containing paradoxes and retains only those that are logically coherent? Physicist Kip Thorne and his student Igor Novikov explored this question with great care in the 1990s, examining specific scenarios involving billiard balls traveling through wormhole time machines. They found that for every paradoxical trajectory, where a billiard ball enters the wormhole and knocks its past self off course so that it never enters the wormhole, there existed at least one self-consistent trajectory, where the ball's journey through the wormhole produces a deflection that is consistent with its original entry. The self-consistent solutions always existed. The paradoxes could always be avoided. But this does not explain why the universe would choose the self-consistent solutions over the paradoxical ones. In classical physics, both solutions satisfy the equations of motion. There is no mathematical reason to prefer one over the other. Something else, something beyond classical general relativity, would need to explain the selection. This something else, many physicists believe, is quantum mechanics. In the quantum world, all possible histories contribute to the probability of an outcome. The path integral formulation of quantum mechanics, developed by Richard Feynman, sums over all possible trajectories that a particle can take, weighting each one by a phase factor determined by the action along that path. In this framework, paradoxical histories would interfere destructively, canceling themselves out, while self-consistent histories would survive and determine the observed reality. It is an elegant resolution, but it has never been proven. The full quantum mechanical treatment of wormhole time machines requires a theory of quantum gravity that we do not possess. And so the question remains, would the universe enforce consistency through some cosmic sleight of hand, or would it simply refuse to allow the situation to arise in the first place, destroying the wormhole before the paradox could form? Hawking clearly favored the second option. His chronology protection conjecture is a bet that the universe takes the brute force approach, annihilating the time machine rather than bothering with the subtle dance of self-consistent histories. The vacuum fluctuations build up, the energies diverge, the wormhole collapses, and the paradox is prevented by the simple expedient of removing the means to create it. It is a violent solution, but the universe has never been squeamish about violence. What science fiction gets wrong? We cannot leave this topic without addressing the elephant in the room, or rather, the wormhole on the screen. Science fiction has done more to popularize the concept of wormholes than any physics paper ever written. From Star Trek to Stargate, from Interstellar to Contact, wormholes have been depicted as luminous tunnels, swirling vortices, and shimmering portals, always beautiful, always convenient, always leading somewhere interesting. The reality, as we have seen, is almost comically different. In Christopher Nolan's Interstellar, which employed Kip Thorne himself as a scientific consultant, the wormhole is depicted as a sphere, which is actually correct. A wormhole mouth in three-dimensional space would indeed appear as a sphere, not as a flat circle or a swirling disk. When you look at it, you would see light from the other end of the wormhole, distorted and curved by the extreme geometry of the tunnel, creating a mesmerizing and deeply disorienting visual effect. Thorne and a team of visual effects artists at Double Negative spent months developing physically accurate renderings of what a wormhole would actually look like, and the results were both stunning and deeply alien. The image you would see through a wormhole is not a simple window to another place. It is a fisheye distortion of an entire hemisphere of sky, compressed and stretched and wrapped around the spherical mouth, with rings and arcs of light tracing the paths of photons that have been bent by the wormhole's geometry. But even Interstellar, for all its scientific rigor, glosses over the fundamental problems. The characters pass through the wormhole without experiencing lethal tidal forces, which is theoretically possible for a sufficiently large and well-engineered wormhole, but the film never addresses the exotic matter that would be required to hold it open. The wormhole in the film was placed near Saturn by a mysterious, advanced civilization, and the characters simply accepted it as a gift. The nightmarish engineering challenges were hand-waved away by attributing them to beings whose capabilities transcend human understanding. This is the fundamental tension between science fiction and science. Fiction needs the wormhole to work because the story depends on it. Physics keeps discovering reasons why it cannot. And so a gap opens between the public imagination, where wormholes are luminous doorways to adventure, and the scientific reality, where they are graveyards of ambition. The truth lies somewhere in the middle, in a place of honest uncertainty. We do not know that wormholes are impossible. We know that every pathway to building one that we have yet discovered is blocked by seemingly insurmountable obstacles. We know that the universe appears to have stacked the deck against them with a thoroughness that suggests either deep principle or cosmic bad luck. But we also know that our understanding of physics is incomplete, and that the complete theory of quantum gravity, whatever it turns out to be, may contain surprises that shatter our current assumptions. Until then, wormholes remain what they have always been, the most beautiful nightmares in all of physics. Structures that the equations permit and the universe denies. Tunnels that exist in mathematics and dissolve in reality. Shortcuts that lead, inevitably and mercilessly, to dead ends. But the beauty of the nightmare is that it keeps us looking. It keeps us questioning. It keeps us pushing the equations further, asking harder questions, reaching for deeper truths. And in the end, that is what physics is for, not to build wormholes, but to understand the universe that forbids them. And what a universe it is. What you would see inside the tunnel. If, somehow, you survived all of these hazards, if the exotic matter held, if the tidal forces were tamed, if the radiation was managed, what would you actually see as you traveled through a wormhole? The answer is both spectacular and profoundly disorienting. As you approach the wormhole's entrance, you would see it as a sphere hanging in space, blazing with the light of the destination on the other side. The image would not be a simple window. It would be grotesquely distorted, like looking through a crystal ball filled with curved mirrors. The light from the far side of the wormhole would be gravitationally lensed, bent and twisted by the extreme curvature of space-time around the throat, creating a kaleidoscopic fisheye view of an alien sky. Behind the wormhole, the stars of your home sky would also be distorted. Light passing near the wormhole mouth would be deflected, creating a halo effect similar to what is seen around black holes. Stars that should be hidden behind the wormhole would appear to swing around its edges, their images smeared into bright arcs and rings by gravitational lensing. The net effect would be stunning and deeply unsettling, as if reality itself had been put through a blender. As you entered the tunnel, the view would change dramatically. The sphere of the entrance behind you would shrink, showing a receding, distorted view of the universe you left behind. Ahead of you, the sphere of the exit would grow, showing an expanding, equally distorted view of your destination. For a brief period, you would be able to see both the origin and the destination simultaneously, each one compressed into a circle of warped light at either end of the tunnel. The walls of the tunnel itself, if walls is even the right word for a region of curved space-time, would not be visible in any conventional sense. There would be no physical surface to see, no rock or metal lining. Instead, you would perceive the walls as a distortion of the images at either end, a region where the geometry of space-time bends the light paths so severely that the images of both universes merge and blur. Depending on the geometry of the wormhole, this could create stunning visual phenomena, concentric rings of light, spiraling patterns, and rainbow-like spectral effects as different wavelengths of light are bent by different amounts. Kip Thorne and the visual effects team at Double Negative created physically accurate renderings of these views for the film Interstellar, and the results were so striking that they generated genuine scientific publications. The wormhole's visual appearance is not just a matter of artistic interpretation. It is a calculable consequence of general relativity, as precise and deterministic as the orbit of a planet. Every arc of light, every ring, every distortion can be traced back to the exact curvature of space-time around the wormhole's throat. It would be, by any measure, one of the most extraordinary sights in the universe. And also, in all likelihood, one of the last things you ever saw. But even if the visual splendor did not kill you, the passage would have deeper consequences, ones that go beyond the physical and into the very nature of time itself. The time machine you did not ask for. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that dismantled humanity's understanding of time. The paper described what would become known as special relativity, and among its many revolutionary conclusions was one that still has the power to unsettle. Time is not absolute. Two observers moving at different speeds will measure time passing at different rates. A clock on a speeding spaceship ticks more slowly than an identical clock sitting still on Earth. This is not an illusion or a trick of measurement. Time genuinely passes at different rates depending on how fast you are moving. The effect is called time dilation, and it has been confirmed with atomic clocks flown on aircraft, with particles accelerated in colliders, and with GPS satellites whose onboard clocks must be corrected for relativistic effects to maintain accurate navigation. Now, imagine you have built your traversable wormhole. Both mouths of the wormhole, the entrance and the exit, float in space, separated by some distance. You can travel through the wormhole's internal tunnel and emerge at the other end, or you can fly through normal space from one mouth to the other. Either way, you get from point A to point B. But now suppose you take one end of the wormhole, mouth B, and accelerate it to nearly the speed of light. You send it on a journey, a round trip through the cosmos at relativistic speeds, and then bring it back. Because of time dilation, the accelerated mouth experiences time differently from the stationary mouth. The clock at mouth B has ticked more slowly. When the journey is complete, the two mouths of the wormhole are no longer synchronized. Mouth A has experienced, say, 10 years. Mouth B, having traveled at nearly the speed of light, might have experienced only 1 year. Here is where things get frightening. The interior of the wormhole, the tunnel that connects the two mouths, does not care about what happened to the mouths externally. Inside the wormhole, the two ends are still directly connected. If you step through the wormhole from mouth A to mouth B, you cross a short distance through the tunnel and emerge at mouth B. But mouth B's clock is 9 years behind mouth A's clock. You step through the wormhole and arrive 9 years in the past. If you then travel outside the wormhole through normal space, back to mouth A, and if that journey takes less than 9 years, you arrive at mouth A before you left. You have traveled backward in time. This is not speculation. This is not a quirky footnote or an unlikely loophole. This is a direct, mathematical consequence of combining special relativity's time dilation with a functioning, traversable wormhole. If the universe allows traversable wormholes, it automatically allows time machines. The two are inseparable. You cannot have one without the other. And time travel, as anyone who has spent more than 30 seconds thinking about it will tell you, is a catastrophic mess. Consider the simplest version of the problem. You have a machine that creates a wormhole. You turn the wormhole on. You travel through it into the past. You arrive at a time before the wormhole existed, and you destroy the machine. You smash it with a hammer. You throw it into a furnace. You detonate a bomb and reduce it to atoms. But if the machine is destroyed, the wormhole was never created. And if the wormhole was never created, you never traveled through it into the past. And if you never traveled into the past, you never destroyed the machine. So the machine exists. So the wormhole exists. So you travel through it and destroy the machine. And around you go, trapped in a logical loop that has no resolution. This is a variation of the grandfather paradox, one of the most famous thought experiments in philosophy and physics. It asks, what happens if you travel back in time and prevent the conditions that led to your time travel? The answer, in most formulations, is that the universe simply breaks. Cause and effect dissolve. Logic collapses. And so, anyone who has deeply studied wormholes has been forced to confront the time travel problem, because a traversable wormhole is a time machine in disguise. Several approaches have been proposed to deal with this nightmare, and none of them are entirely satisfying. Novikov, the same Soviet physicist who first described white holes, developed what he called the self-consistency principle. He suggested that time travel might be permitted, but only in cases where the past remains unchanged. Imagine you throw an asteroid toward the entrance of a wormhole. At the last moment, another asteroid flies out of the wormhole and knocks yours off course. Your asteroid still enters the wormhole, but on a different trajectory than you intended. It travels through the tunnel, emerges in the past, and collides with itself, creating the very deflection that altered its course in the first place. The history of the universe remains self-consistent. The past is not changed. Some unknown mechanism ensures that paradoxes simply cannot occur. It is an elegant idea, but it raises more questions than it answers. What is this mechanism? How does the universe know to prevent paradoxes? Is there some cosmic referee standing guard at the entrance of every wormhole, rearranging events to preserve logical consistency? Novikov's principle describes the what, but not the how, and many physicists find it deeply unsatisfying. Stephen Hawking took a more drastic approach. In 1992, he proposed what he called the chronology protection conjecture, a hypothesis that the laws of physics themselves actively prevent the formation of time machines. Hawking's idea was based on calculations showing that as a wormhole approaches the conditions necessary for time travel, quantum effects become increasingly violent. Virtual particles in the quantum vacuum, the same sorts of fluctuations that produce the Casimir effect, begin to pile up at the wormhole's throat. Their energies grow and grow, amplifying with each loop through the time-shifted tunnel, building like audio feedback in a microphone until they reach catastrophic levels. The energy surge, Hawking argued, would destroy the wormhole at the precise moment it became capable of functioning as a time machine. The universe would not allow the paradox to form because it would blow up the device before the paradox could occur. As he put it, with characteristic wit, it seems that there is a chronology protection agency which prevents the appearance of closed time-like curves and so makes the universe safe for historians. Hawking himself was not entirely certain that his conjecture was correct. The calculations that predict the energy buildup rely on semi-classical gravity, an approximation that combines general relativity with quantum mechanics in a way that is known to break down at very high energies. To truly settle the question, you would need a complete theory of quantum gravity, a unified framework that merges Einstein's space-time geometry with the full machinery of quantum field theory. We do not have such a theory, and until we do, the fate of wormhole time machines remains unresolved. There is, however, a third possibility, one that is as mind-bending as anything else in this story. What if wormholes do allow time travel, but not to your own past? What if, instead, they connect you to the past of a different universe entirely? In the many-worlds interpretation of quantum mechanics, first proposed by Hugh Everett in 1957, every quantum event causes the universe to branch. When a particle has a 50-50 chance of spinning clockwise or counterclockwise, both outcomes occur, each in its own separate universe. The multiverse is an infinitely expanding tree of realities, with new branches sprouting at every quantum decision point. If this interpretation is correct, and it has not been definitively ruled out by any experiment, then wormholes might connect not to the past of our own universe, but to the past of a different branch. You step through the wormhole and emerge in a universe where everything is identical to your past, except that you are now present in it. In that universe, you can do whatever you want, destroy the wormhole machine, prevent your own birth, rearrange history. None of it affects the universe you came from. Paradoxes are avoided because the past you are visiting is not your past. It is someone else's. In such a scenario, Hawking's party for time travelers might have actually been a smashing success, just not in our universe. In some other branch of the quantum tree, revelers from the future showed up with champagne and stories. In our branch, the room stayed empty. the chronology protection conjecture holds in our universe. Time travel is allowed in the multiverse. This is a beautiful idea, but it is also entirely speculative. We have no evidence for the many worlds interpretation beyond the mathematical elegance of the framework. We have no evidence for wormholes connecting different branches of the multiverse. And we have no evidence that the multiverse exists at all. What we do have is a profound and deeply uncomfortable conclusion. If traversable wormholes exist, they bring time travel along for the ride. And time travel brings paradoxes, and paradoxes bring either the destruction of the wormhole or a wholesale revision of our understanding of causality and the structure of reality itself. That is nightmare number 3. But we are not done yet. Because even if you somehow solved every single problem we have discussed so far, even if you found exotic matter, stabilized the tunnel, avoided the time paradoxes, and survived the journey, you might still find that your wormhole is not the cosmic shortcut you were hoping for. In fact, it might be the worst shortcut ever conceived. The shortcut that is longer than the long way. In 2019, physicists Daniel Jeffries, Ping Gao, and Aaron Wall published a result that should have been cause for celebration and instead delivered one of the most deflating punchlines in the history of theoretical physics. They had found a way to make a traversable wormhole without exotic matter. Let that sink in for a moment. For 3 decades, ever since Thorne's 1988 paper, the central obstacle to building a traversable wormhole had been the requirement for negative energy or exotic matter, a substance that violated the energy conditions and might not exist. And now, using sophisticated tools from quantum field theory and the mathematics of the gauge/gravity duality, Jeffries and his colleagues had shown that you could construct a wormhole that was stable and traversable using only the quantum effects of ordinary matter, effects similar in spirit to the Casimir effect, but generated by the entanglement between the 2 mouths of the wormhole itself. There was no need for impossible ingredients. No need for energy conditions to be violated on a macroscopic scale. The wormhole could, in principle, exist within the known laws of physics. But there was a catch so devastating that Jeffries himself described it with almost comedic understatement. It takes longer to get through these wormholes than to go directly, so they are not very useful for space travel. The wormhole was slower than just flying through regular space. Not a little slower, not marginally slower. Paths flowing through the wormhole were longer and slower than paths that remained in flat spacetime. The shortcut was, in fact, a long cut. The tunnel through spacetime took more time to traverse than the journey around it. Building this wormhole would be not just pointless as a means of transportation. It would be actively counterproductive. It would be worse than not building one at all. To be fair to Jeffries and his colleagues, their analysis used a modified structure of spacetime, a special mathematical framework called anti-de Sitter space that has only 2 spatial dimensions and 1 of time. This is not the same as the physical universe we inhabit, which has 3 spatial dimensions and 1 of time. Their result might not directly apply to a wormhole in our universe, but it hints at a deeply frustrating possibility that the universe might allow wormholes, might even make them relatively easy to build compared to the exotic matter-fueled monsters of Thorne's design, but that it hobbles them with a cosmic speed limit that renders them useless. Nature, it seems, might have one final trick up its sleeve. Not the outright prohibition of wormholes, not the catastrophic instability, not the time paradoxes, but something almost crueler, permission granted, but with conditions that make the permission meaningless. Imagine saving up for years to buy the fastest car in the world, building a track specifically designed for it, and then discovering that the car can only move at the speed of a slow walk. The wormhole exists. The tunnel is open. You can travel through it, and it takes you longer to get there than if you had never bothered. This is perhaps the most deflating of all the nightmares associated with real wormholes, because it does not rely on unknown physics or unproven conjectures. It does not require exotic matter or violations of energy conditions. It emerges naturally from the mathematics of a consistent, well-understood framework. It might simply be a feature of the universe that shortcuts through space-time are not, and cannot be, actual shortcuts. Quantum ghosts and entangled bridges. We have traveled through a gauntlet of nightmares. Wormholes that collapse faster than light. Exotic matter that might not exist. Time paradoxes that could unravel causality. Tunnels that are slower than the scenic route. At this point, you might reasonably wonder, why do physicists keep studying these things? The answer reveals something beautiful about how science works. Wormholes, even in their impossibility, serve as some of the most powerful tools ever devised for probing the deepest mysteries of the universe. They are not just failed transportation devices. They are windows into the hidden architecture of reality. And in recent years, wormholes have experienced a dramatic scientific renaissance, not as practical engineering projects, but as theoretical keys to unlocking the relationship between gravity and quantum mechanics, the two great pillars of modern physics that have stubbornly refused to merge into a single coherent framework for nearly a century. The story begins in 2013, when two of the most brilliant theoretical physicists alive, one Mel DeSena of the Institute for Advanced Study and Leonard Susskind of Stanford University, proposed one of the most audacious ideas in the history of physics. They called it ER equals EPR. To understand what this means, we need to revisit 1935, the same remarkable year that produced the Einstein-Rosen bridge. That same year, Einstein published a second groundbreaking paper, this one co-authored with Boris Podolsky and Nathan Rosen. Yes, the same Nathan Rosen. This paper, known as the EPR paper, described a bizarre property of quantum mechanics that Einstein found deeply disturbing: quantum entanglement. Entanglement occurs when two particles become linked in such a way that the quantum state of one instantly determines the quantum state of the other, regardless of the distance separating them. If you measure one particle and find it spinning clockwise, the other particle, whether it is across the room or across the galaxy, is instantaneously determined to be spinning counterclockwise. Einstein called this spooky action at a distance and considered it evidence that quantum mechanics was incomplete. But entanglement has been confirmed in thousands of experiments since then. It is as real as the ground beneath your feet. In their 2013 paper, Cool Horizons for Entangled Black Holes, Mel DeSena and Susskind proposed something breathtaking: that the Einstein-Rosen bridge, ER, and quantum entanglement, EPR, are not just related concepts. They are the same thing. Every pair of entangled particles is connected by a wormhole. Every wormhole is a manifestation of entanglement. ER equals EPR. These are not the traversable wormholes of science fiction. They are non-traversable quantum bridges, gossamer filaments of space-time geometry so small and so quantum mechanical that no information can be sent through them. They do not violate the laws of physics. They do not allow faster-than-light communication. They are invisible, undetectable, and everywhere. If the conjecture is correct, the implications are staggering. It would mean that entanglement, the quantum mechanical phenomenon that Einstein despised, is literally the thread that stitches the universe together. Without entanglement, space-time would not be a smooth, continuous fabric. It would atomize, breaking apart into disconnected fragments. The geometry of the cosmos, the very structure of space and time that allows you to walk across a room or look up at the stars, emerges from the quantum entanglement of particles. As Susskind himself put it, the solid and reliable structure of space-time is due to the ghostly features of entanglement. This idea, which builds on earlier work by physicist Mark van Ramsdonk, has opened an entirely new frontier in theoretical physics. It suggests that general relativity and quantum mechanics are not separate theories in need of unification. They are different descriptions of the same underlying reality, a reality in which geometry is entanglement and entanglement is geometry. And wormholes, those impossible, nightmarish tunnels through space-time, are the Rosetta Stone that allowed physicists to see this connection. In 2017, building on the ER equals EPR framework, Ping Gao, Daniel Jafferys, and Aaron Wall showed that a new kind of traversable wormhole could exist, one that did not require exotic matter. Instead, the negative energy needed to hold the wormhole open was generated by the quantum entanglement between the two mouths. The wormhole was stabilized not by some impossible material, but by the same quantum correlations that connect every entangled particle in the universe. This discovery was not about building starships. It was about solving one of the deepest puzzles in physics, the black hole information paradox. Since the 1970s, when Stephen Hawking discovered that black holes emit radiation and slowly evaporate, physicists have grappled with a terrifying question. If a black hole absorbs information in the form of particles, atoms, and patterns of matter, and then evaporates away into featureless radiation, where does the information go? Quantum mechanics insists that information can never be truly destroyed. The rules of quantum physics are, at their core, deterministic and reversible. If you know the current state of a system, you can, in principle, reconstruct its entire history. But if a black hole erases information, quantum mechanics is wrong. And if quantum mechanics is right, then something very strange must be happening at the event horizon. The new traversable wormholes offered a possible resolution. If an observer falls into a black hole, the information they carry is not destroyed. Instead, it flows through a quantum wormhole, an ER bridge generated by the entanglement between the black hole and its Hawking radiation, and emerges on the other side. The observer can, in principle, escape through the wormhole and tell their story. As the physicist John Preskill, a leading expert on quantum gravity, put it, "What I really like is that an observer can enter the black hole and then escape to tell about what she saw." This suggests that black hole interiors really do exist, that space-time continues beyond the event horizon, and that the information paradox is not a fatal flaw in our understanding of physics, but a signpost pointing toward the deeper unity of gravity and quantum mechanics. The foam beneath reality. There is one more layer to this story, one that takes us down to the very bottom of reality, to scales so small that space and time themselves lose their meaning. John Wheeler, the man who named wormholes, had another vision. He proposed that at the smallest conceivable scales, far below the size of atoms, far below the size of protons and quarks, at a distance called the Planck length, roughly 0.00016 meters, the smooth fabric of space-time breaks down. At this scale, the gentle curvature of space that we associate with gravity becomes a roiling, frothing chaos. Space-time buckles and tears, forming and destroying tiny structures, among them minuscule wormholes, in a ceaseless quantum storm. Wheeler called this the quantum foam, and the idea has persisted for nearly 70 years as one of the most evocative images in theoretical physics. In the quantum foam picture, space-time is not a smooth continuum at the smallest scales. It is a seething ocean of fluctuations, with wormholes popping into and out of existence like bubbles in a pot of boiling water. These wormholes are unimaginably small, existing for unimaginably brief durations, completely invisible to any technology we possess or are likely to possess. But Thorne, in his 1988 paper, made a tantalizing suggestion. What if an advanced civilization could reach down into this quantum foam and pluck out one of these submicroscopic wormholes? What if they could carefully enlarge it, inflating it from the Planck scale to macroscopic proportions, stabilizing it with negative energy or some exotic quantum effect, and fashioning it into a usable tunnel? The idea is wildly speculative. We do not know if the quantum foam exists in the form Wheeler described. We do not know if it contains wormholes. We do not know if it is possible to extract structures from it. And even if all of these things were possible, we do not know if a Planck-scale wormhole could be enlarged without destroying it. But the mere possibility has kept the dream alive. Somewhere in the basement of reality, in the foundations of space-time itself, there might be wormholes. Trillions upon trillions of them, churning in the quantum depths, too small to be seen and too brief to be measured. And if our understanding of physics advances far enough, if we develop the technology and the knowledge to reach down into that foam and pull something out, perhaps, just perhaps, we could build the tunnel after all. It is a hope built on speculation, wrapped in uncertainty, and surrounded by nightmares. But it is not, strictly speaking, impossible. And in physics, not impossible is sometimes enough. What the nightmares teach us. Let us step back and look at the full picture. You want to build a wormhole. Here is what you face. First, the basic Einstein-Rosen bridge, the simplest wormhole that general relativity produces, is not traversable. It collapses faster than the speed of light. Nothing, not even a photon, can make it through before the tunnel destroys itself. If you enter the wormhole, you will be trapped inside a black hole, and the singularity will be the last thing you ever encounter. Second, to make a wormhole traversable, you need to stabilize it with exotic matter or negative energy. Exotic matter has never been observed and would violate the conservation of momentum if it existed. Negative energy exists in tiny, localized quantities through the Casimir effect, but nobody knows if it can be amplified to the scales required for a wormhole. The energy conditions that govern how energy behaves in the real universe would need to be violated on a macroscopic scale, and there is no evidence that this is possible. Third, if you do manage to build a traversable wormhole, it automatically becomes a time machine. The time dilation effects of special relativity mean that the two mouths of the wormhole can become desynchronized, allowing travel into the past. This opens the door to devastating logical paradoxes, and the universe's response, at least according to Hawking's chronology protection conjecture, may be to destroy the wormhole at the precise moment it becomes capable of time travel. Fourth, the tidal forces inside a wormhole are ferocious. The gravitational gradients that permeate the tunnel would stretch and compress anything passing through, potentially ripping it apart at the atomic level. Even if the wormhole is stabilized against overall collapse, the journey through its interior would subject a traveler to extreme gravitational distortion that could be lethal. Fifth, and perhaps most deflating of all, even wormholes that are theoretically stable and traversable and free of exotic matter may turn out to be slower than regular space travel. The universe might allow wormholes, but make them utterly pointless as transportation devices, the cosmic equivalent of digging a tunnel under a hill and discovering that the tunnel is longer than walking over the hill. So why study them? Why pour decades of brilliance and computational power into objects that seem designed by the universe to fail? Because the failures are instructive. Every dead end in wormhole physics has illuminated some deep truth about the nature of reality. The instability of the Einstein-Rosen bridge taught us about the dynamic nature of space-time, that the geometry of the universe is not a static backdrop, but a living, evolving entity that resists being manipulated. The requirement for exotic matter revealed the deep connections between general relativity and quantum field theory, showing that the behavior of gravity at extreme scales is intimately linked to the quantum vacuum. The time travel paradoxes forced physicists to think rigorously about the nature of causality and the direction of time, leading to insights that inform our understanding of everything from quantum computing to the arrow of entropy. And the ER equals EPR conjecture, born directly from the study of wormholes, has opened what may be the most promising pathway to a unified theory of quantum gravity that physics has ever discovered. Wormholes are nightmares, but they are nightmares that teach us about the deepest layers of reality, about the relationship between space, time, matter, and information, about the rules the universe has set for itself and the consequences of trying to break them. As Stephen Hawking himself said, reflecting on the difficulties of understanding wormholes, time travel, and quantum gravity, not only does God play dice, but he sometimes throws them where they cannot be seen. The dice are still rolling. The full theory of quantum gravity remains elusive. And until it arrives, we cannot say with certainty whether wormholes are absolutely forbidden or merely fiendishly difficult. What we can say is that the universe has stacked the deck against them with a thoroughness that borders on malice. Every route to a working wormhole runs through a gauntlet of physical impossibilities, logical paradoxes, and mathematical dead ends. And yet, in the foundations of reality, in the quantum foam that John Wheeler imagined bubbling at the Planck scale, there might be wormholes everywhere, tiny and fleeting, connecting every point in the universe to every other point through an invisible network of geometric bridges. Not useful for travel, not useful for communication, but real, in some quantum sense, as threads in the fabric that holds the cosmos together. It is a strange and humbling thought. The shortcuts are everywhere, built into the very bones of space-time. And they are all, every single one of them, completely, utterly, and magnificently useless. That is the joke the universe is playing on us. The tunnels exist. The bridges are real. And they are the most beautiful dead ends in all of physics. Standing at the edge. So let us return to where we began. You are standing at the mouth of a wormhole. The sphere of stolen light hangs before you, shimmering with the distorted image of a far-off piece of the sky. The stars on its surface belong to a place unimaginably distant, a place you could never reach by any conventional means, not in a lifetime, not in 1,000 lifetimes. The wormhole offers you a door to that place, a door that opens through the very geometry of space-time itself. But you know, now, what lies beyond that door? You know about the tidal forces that would tear you apart, the gravitational gradients that would stretch your body into a strand of atoms. You know about the exotic matter that does not exist, the negative energy that cannot be produced, the energy conditions that refuse to be broken. You know about the time paradoxes waiting to ambush you at the exit, the universe's willingness to destroy the tunnel rather than allow the laws of causality to be violated. You know about the possibility that even a perfect wormhole, free of every flaw, might take longer to traverse than simply flying through open space. You know all of this, and yet, standing there, looking into that sphere of impossible light, you feel something that no equation can extinguish and no paradox can suppress. You feel wonder, because the fact that the universe even allows the concept of wormholes, the fact that Einstein's equations can describe tunnels through space and time, the fact that quantum entanglement might be stitching the fabric of reality together through invisible bridges at the Planck scale. These are among the most extraordinary discoveries the human mind has ever made. They tell us that the universe is stranger and more deeply interconnected than we ever imagined. They tell us that the relationship between space, time, gravity, and information is richer and more mysterious than we have yet been able to unravel. And they tell us that even the nightmares of physics, the dead ends, and the impossibilities and the paradoxes are not failures. They are invitations. They are the universe daring us to understand it more deeply. Wormholes may never carry us to distant stars. They may never let us skip across galaxies or race down flights of stairs, as Wheeler would have put it, through tunnels in the fabric of space-time. But they have already carried us somewhere far more important. They have carried us to the edge of our own understanding, to the place where the known laws of physics blur into the unknown, where the answers give way to deeper questions, and where the only way forward is to keep asking. What happens when you get to the end of things? We do not know yet, but we are closer than we have ever been to finding out, and the nightmares along the way have been worth every shudder. Thanks for watching. If you enjoyed this deep dive into the terrifying physics of wormholes, hit that like button and subscribe so you never miss a video. Leave a comment and let us know what you think. Could wormholes ever be made to work? Or has the universe sealed them off for good? We will see you next time. The quantum gravity frontier. We have now seen how wormholes connect to the deepest questions in theoretical physics, from the nature of entanglement to the resolution of the black hole information paradox. But there is a final chapter in this saga that may prove to be the most consequential of all, a chapter that concerns the very foundations of physics itself and the long-sought marriage between gravity and the quantum world. There is a final chapter in the story of wormholes that deserves our attention, one that is still being written as we speak, in the offices and lecture halls and chalk-dusted blackboards of universities around the world. The central problem of modern theoretical physics is the incompatibility of its two greatest theories. General relativity describes gravity as the curvature of space-time. Quantum mechanics describes the behavior of particles through probability waves and quantum fields. Both theories are spectacularly successful within their own domains. General relativity predicts the motion of planets, the bending of light, and the behavior of black holes with extraordinary accuracy. Quantum mechanics predicts the energy levels of atoms, the behavior of semiconductors, and the decay rates of radioactive isotopes with a precision that borders on the magical. But when you try to combine them, when you try to apply quantum mechanics to gravity or describe spacetime at the smallest possible scales, the mathematics breaks down. The equations produce infinite answers. The predictions become nonsensical. The two theories, each flawless on its own, refuse to coexist. This is the problem of quantum gravity, and it has resisted solution for nearly a century. The greatest minds in physics, from Einstein to Hawking to Witten, have grappled with it and come away empty-handed. We have candidate theories, string theory, and loop quantum gravity being the most prominent, but none of them has produced a definitive, experimentally confirmed prediction that would validate it over its competitors. And here is where wormholes become not just nightmares, but invaluable tools. Because wormholes, by their very nature, live at the intersection of general relativity and quantum mechanics. They are gravitational objects, governed by Einstein's equations, but their behavior, their stability, their response to perturbation all depend on quantum effects. The exotic matter that stabilizes them is a quantum phenomenon. The vacuum fluctuations that might destroy them are quantum phenomena. The entanglement that might generate them, according to the ER equals EPR conjecture, is quintessentially quantum. Wormholes are the arena where the two great theories of physics are forced to confront each other. And the results of that confrontation, whatever they turn out to be, will teach us something profound about the nature of reality. Consider the black hole information paradox once more. When Stephen Hawking discovered that black holes radiate, he revealed a conflict between general relativity and quantum mechanics that has not been resolved to this day. General relativity says that anything falling into a black hole is gone forever, sealed behind the event horizon. Quantum mechanics says that information can never be destroyed, that the quantum state of the universe is always preserved. Both cannot be right. Something has to give. The new traversable wormholes, the ones generated by quantum entanglement rather than exotic matter, offer a potential resolution. If information can flow through quantum wormholes, if the bridges that connect entangled particles are real conduits for quantum information, then the information paradox dissolves. The information is not destroyed. It is transmitted through the quantum wormhole network, emerging encoded in the Hawking radiation, invisible to any observer who does not know where to look, but nonetheless preserved. This would be a monumental result. It would not prove that traversable wormholes exist in the sense that a person could walk through one, but it would demonstrate that wormhole-like structures play a fundamental role in the architecture of quantum gravity, that the geometry of space-time and the entanglement of quantum particles are two descriptions of the same underlying reality. Recent work has pushed this idea even further. In 2022, a team of physicists led by Maria Spiropoulou at the California Institute of Technology performed an experiment on Google's Sycamore quantum computer that simulated the quantum dynamics of a simple wormhole. The experiment was highly simplified, involving a toy model of gravity with far fewer dimensions than the real universe, and it did not create an actual wormhole in physical space. But it demonstrated that the mathematical structures associated with wormholes could be instantiated and studied on quantum hardware, opening a new frontier in the experimental study of quantum gravity. The experiment generated considerable excitement and also considerable controversy. Some physicists argued that simulating a wormhole on a quantum computer was no more significant than simulating a roller coaster on a video game, that the simulation captured the mathematics but not the physics. Others countered that in a world where the ER equals EPR conjecture is correct, the distinction between the mathematics and the physics may be less clear than we assume. The debate continues, and it is exactly the kind of debate that advances science. Wormholes, even when they exist only as mathematical models or quantum simulations, serve as lightning rods for the deepest questions in physics. They force us to ask what is real, what is possible, and what lies beyond the boundaries of our current knowledge. And so the nightmare, it turns out, has a silver lining. The same features that make wormholes impossible to travel through may make them indispensable to understanding the universe. The tidal forces that would kill a traveler teach us about the geometry of extreme space-time. The exotic matter that no one can find teaches us about the energy conditions and their quantum violations. The time paradoxes that would unravel causality teach us about the arrow of time and the nature of quantum consistency. And the quantum wormholes that connect entangled particles teach us about the most fundamental relationship in all of physics, the relationship between gravity and information. In a very real sense, wormholes are not destinations. They are questions, and the questions they ask about the nature of space, time, gravity, and the quantum world are the most important questions that physics has ever faced. We may never travel through a wormhole, but we are, right now, thinking through them. And in the end, that may matter more than any journey across the stars.